All right, class. Good morning once again. So this morning we are going to actually have our first official lecture in this class and in this course, sorry. And what we're going to do is we are going to essentially speak to the first portion of the course, which deals with spectroscopy, vibrational spectroscopy. So without further ado, let's begin. Of course, as I get into the class, I'll be giving you more details with regards to the course outline and where we are and those types of things in terms of the calendar and the dates that you need to be mindful of. All right, so first of all, welcome to the class. Today we are speaking about spectroscopic techniques for determination of molecular structure, course titled Chem 3205. My screen share is paused. Why is that? Stop sharing and share again. Okay. What's going on there? All right, just bear with me a little bit. Let's see what's happening. Right, so welcome to Chem 3205, take 2. First class, take 2. And we are about to have our conversation regarding the first portion of the course, which deals with vibrational spectroscopy. So to start this process, we are going to actually have a brief outlay in terms of our course mapping. Now, I am going to post the updated draft of the course outline. As you're familiar with my style, I like to give you guys a mapping of the topics and sort of break it down as much as possible with regards to dates, so that you can have as effective a possible method of possible of in terms of being able to organize yourselves and positioning yourselves with regards to study and so on. Before I go further, I do need to make mention that in a discussion with the HOD, one of the things that we have decided is that for this particular course, there will be a slight adjustment in the weighting of the course. So as you would have noticed before, this is a course that originally would have had a 40% coursework weighting and a 60% final exam weighting. And so in the adjustment that's being made is we're actually going to not reverse, but we're going to switch those two, which means that your coursework will carry the 60% weight and your final exam will carry the 40%. All right, so that actually gives you guys a good opportunity to be able to hunker down and really fight for this A. There's no reason why you all can't get an A in this class. And as much as is possible, I am here to facilitate that process, but you're the one that will do the walking. All right, so the first few lectures, as you know, we meet for 2 hours a week. And so essentially what it means is that our time per week will be covering two lecture hours. And as it currently stands, our mapping for the next 4 hours of class is as is seen on the screen. So you will have an introduction to spec, and then you'll also have an introduction to vibrational spectroscopy, followed by infrared spectroscopy specifically, and then the absorption of radiation of molecular vibrations and selection routes. I'm not sure how much of that we will get to today, given all the issues that we've experienced thus far. But it is my hope that we will be able to get as far as we can. And there are some video resources that I will refer you to that will help to bring out some of the concepts. So for today, our focal point will be lecture hours 1 and 2. And as we pick up from there, we will pick up with hours 3 and 4 in our subsequent meeting. All right, so the big question of what is spectroscopy is an important question to ask. And it's important for you as you are encountering various disciplines to always keep a vocabulary list, because the reality is that as you engage with the material, you'll find that your vocabulary will have to expand to accommodate the language that that discipline is actually involved in, or involves that language that discipline involves. So for that, our first question of what is spectroscopy basically introduces to us a vocabulary word that we would not have been exposed to previously in our everyday language. And you know what? It's interesting because there are times when you come across words so often, you assume you know the meaning of them simply because you hear them so regularly. But this is one of the things I would like to caution you all about. Do not make the assumption that because you are familiar with something in terms of hearing it, that automatically means that you know what it means. All right? It's important to get the definitive particulars that define that particular issue, term, language, vocabulary, concept, whatever. And if it is the case that it repeats what you've already learned, great. But if it isn't, you would have lost nothing. You would have gained, actually. So, of course, when we hear spectroscopy, essentially what we are saying is that we know that we have to engage the use of spectra and the interpretation of spectra. But the question of what type of spectra is important and why, okay? So essentially, one of the things that we must note is that spectroscopy is the study of the effect or its resulting impact of energy on matter. All that entails, all that is involved in the interaction of energy with matter is included in the study of spectroscopy. Of course, there are various aspects of it. There is the instrumentation component in terms of how the instruments work, what are the detectors, what radiation is being detected, where do those levels, where do those bands of radiation exist on our grand electromagnetic spectrum as we interface with it. All right, so here we have a picture of the electromagnetic spectrum, and you can see that it actually is comprised of several varying groups and categories of radiation. What you have on the far left is the grouping that is comprised of our low frequency waves or radiation, and those are inclusive of what we call radio waves. Everybody's familiar with a radio, and you know what radios are able to do. One of the main transmissions that they convey is sound signals, and it's actually a communication tool. But there are also communication tools that engage radio waves from a different perspective that is not everyday use for the average person. We have microwaves, which find utility in food industry and food preparation. And the reason they're able to do that is because of the nature of the wave, again, the frequency / wavelength, and the corresponding energy that is included in that form of radiation. Moving to the right, we have our infrared radiation. As you can see, it's between 10 to the -3 and 10 to the -5, thereabouts on the spectrum. And at this point in the conversation, At this point in the conversation, I'm not going to focus as much on the values of the actual radiation that is before us. Right now, we're just introducing it, so I'm giving you more the categories of uses as they and their corresponding positioning on the spectrum itself. So infrared radiation is one of those that we're actually going to give some attention to today if we get time. But as you are aware, from radio waves all the way to infrared, all of these forms of radiation are invisible. They're not visible to the naked eye. They are detectable, but they're not. Our interaction with these types of radiation is not by virtue of our ability to see them with our naked eyes. All right, so it then means that the detectors that we have to engage to identify their presence have to actually include a different mechanism to be able to verify their presence. And so that's a part of what we're going to have our discussion on. All right, to the right of the infrared region is the visible light region, and everybody is familiar with this. The red, orange, yellow, green, blue, indigo, violet range of radiation or light actually exists in this region. This is what we refer to as visible light or white light. And essentially it includes the full spectrum going from red to violet. And you can see that as well. Here you have the infrared region, which is invisible. And then on the right of our visible region, we have the violet, we have ultraviolet radiation. So on our far left of visible light is the red, and on our far right is the violet. So essentially, that gives you a clue as to also positioning and ordering of the actual radiation bands if you want to know them and if you need to know them with regards to how they occur. A clue or a little tag that will help you to remember is that infrared is the region that is just before the red wavelength of light in white light. And then ultraviolet is that band of radiation that is just after the violet end of white light, okay? That also gives us clues as it pertains to energetics, because as we move from low frequency radiation to high frequency radiation, what happens is we are actually increasing our energy, the energy of the radiation that is encapsulated in those bands. Okay, so moving forward, we have the ultraviolet band of radiation, which is an invisible band. When I say invisible, I mean it is not detectable by human beings using the naked eye. And so essentially we have literally left the visible region again, and we're now going into the invisible components of the electromagnetic spectrum. Ultraviolet rays, you're familiar with them. They actually originate with the sun, from the sun. In fact, the greater portion of this electromagnetic spectrum emerges from the sun, and I'll say a little bit more about that. Following the ultraviolet region are your X-rays and your gamma rays. And again, as you can see, moving from left to right, we are increasing in our frequency of the radiation that we are actually demonstrating here, as well as we are increasing in our energy. At the same time, as you increase your frequency, you are decreasing your wavelength, okay? So always keep that in mind. So to summarize that, what we're basically saying is that the energy is transmitted through space. Electromagnetic radiation is transmitted through space in visible and invisible forms, and essentially it originates from a source emitter. The largest source emitter that we have on Earth is the sun. Of course, when the source emitter transmits the energy by pushing it through space, for want of a better word, that process is what we refer to as radiation. All right, so the question of how is it that the heat from the sun is transmitted from where it is several billion miles away to Earth is answered by this actual statement here, where if the fact that the sun exists at that distance from the Earth itself suggests that it actually could stay there with its heat, and yet we are actually able to experience the effects of the heat of the sun as well as the light here on Earth, even though we're separated by distance. The only possible way that that can occur is by way of the process known as radiation. And this radiation, while it's a term that you've heard very often, almost ubiquitously, it's constantly being used, it's a word that literally indicates the process of transferal of this energy or transmission of this energy from the source emitter to the receiver. In this particular case, here on Earth, we are the receivers, basically, right? And so every form of radiation that is presented here on this spectrum is literally transmitted or propagated from its source to the actual receiver by way of the process that we have highlighted here. All right, so I already said that we know that the sun does what it does. It transmits light and it transmits heat, and it also transmits all the other forms of radiation that is presented here. However, there is, I shouldn't say it like that. I would say to you that from the infrared region all the way to the right, this is where our sun is actually conveying energy or transmitting energy to the Earth. To the left of the infrared region, those forms of radiation are actually artificial and they're man-made. And so kindly make a note of that, because there is a distinction. They all are a part of the electromagnetic spectrum, but they are not necessarily all originating from the same source, okay? So just bear that in mind. All right, so the waves, like I said, from the sun are actually high frequency and they're electromagnetic in their nature. And so that speaks to two things in terms of characteristics and parameters. Like I alluded to before, high frequency waves are high energy waves. And the fact that they're high energy means then that they're able to actually have significant impact on the matter that they interact with. So when these various forms of radiation come in contact with matter, the corresponding effect is significant because of the level of energy that these radiation bands are actually carrying or encapsulating. Of course, you are not unfamiliar to that concept, and you will see as we go further how the various bands have varying impacts in terms of their interactions, which is the spectroscopy component that we're looking at. The second characteristic of these energy waves is that they're electromagnetic in nature. And so for you to understand what that means, this is where you would have to rely on your old physics class to remember what that essentially entails. So an electromagnetic wave is a wave that is transverse, and it is a composite of two components. It's a composite of an electronic field vector and a magnetic field vector. These vectors are both components of this transverse wave, but they exist in orthogonal planes. So as you can see here, if we look at the red wave, we can see that it exists in the XY plane. And if we look at the blue wave, it exists in the XZ plane. Now, these planes that we have here are actually arbitrary assignments. It's not necessarily the case that one would have to say specifically in this case, this situation, that the electric component is in the XY plane all the time, or the magnetic component is in the XZ plane all the time. That is not what we are giving attention to in this particular course. But what is important for you to note is that electromagnetic waves comprise two components of two vector fields. And these vector fields are actually propagators of the fields of these varying types. All right. Now, where your physics comes in is you will recall that every charge has a corresponding magnetic component to it. And so it doesn't matter what's the size of the charge, it doesn't matter how minuscule the charge is, there is going to be a corresponding magnetic component that accompanies it. And so the reason then why this is significant for us is because when we are interacting with waves, or when we are considering, the interaction of these electromagnetic waves with matter, we would have to consider the fact that the waves have this nature of being electromagnetic, and that matter also has the nature of being electromagnetic. Reason being that matter has electrons. Matter, every form of organic matter on Earth comprises, well, not even just organic, every form of matter on Earth comprises electrons. And electrons are charged particles that also have wave duality. But being charged particles, that would mean that they have a corresponding magnetic component as well. All right, so at this point, I'm going to ask you all to type a Y in the chat if you are clear on that concept, or if that is something that you need to be repeated in any way. Let me hear from you at this time, please. All right, great. So this is a concept that basically you're familiar with, and you know essentially that when the interaction then is taking place between your electromagnetic wave and the matter that it is encountering, that interaction is literally electromagnetic to electromagnetic. And that then has an effect on whether or not that radiation that is coming towards the piece of matter, whether it's a human being or plant or the ground or whatever, that interaction is going to lead to an absorption and a corresponding transmission, depending on the nature of the radiation that is coming in contact with it. All right. Now, as the two fields are propagated throughout space or through space, what's happening is they do so in a manner that is fluctuating. And what that then leads to is an oscillatory or periodic process. So that then is what is responsible for the picture that we see here. It means then that if we consider the definition of a vector is actually something that has magnitude and direction. And so the x-axis indicates the direction in which the radiation is being propagated. Okay, so it's moving from point 0 to x, let's just say, on the x-axis, and it's traveling along the path of the x-axis. So that speaks to the direction. However, in terms of the magnitude, as you can see, the value of the propagation is constantly increasing. It increases up to this point, reaches a crest, and then it begins to decrease and goes to what we call a trough. And as it's going to this trough, it reaches this minimum basically, and then begins to travel up in terms of quantity again. And this quantity keeps fluctuating over time. So as the wave is being propagated, let's say this is the source, the sun, and this is the earth. In going from the source to the receiver, the transmission is in such a way whereby the direction is constant, the speed of the propagation is constant, but the magnitude is varying over time. However, even though the magnitude is varying, it is actually varying within limits. And so that is what constitutes the wave-like nature of the radiation that we are describing or talking about. All right, so the same thing is happening electronically as well as magnetically. However, the nature of the magnetic component of your electromagnetic wave is a little bit different in its interaction than how the electronic component of your electromagnetic wave is when it interacts with matter. Right, so the electrical field component of our electromagnetic wave interacts with charged particles, whether or not they are stationary or in motion. On the other hand, the magnetic component acts only on charged particles that are in motion. So if a particle is stationary, the magnetic component will not interact with it, or it will not impact it. And so that then has an outcome or a resulting effect in terms of what type of absorption properties would be exhibited when the interaction takes place between the electromagnetic radiation and the piece of matter that it is interfacing with. All right, so all of the sun's energy rays will exist as part of this wide range of measurable frequencies, and the wavelengths, as we said, travel at the speed of light, and they do so constantly. So there's no fluctuation as they're traveling from the sun to the earth or from the source to the receiver. There's no fluctuation in terms of speed. However, what fluctuates is the field strength as the transmission is taking place. So like I said before, on the left, what we have are our artificial sources of radiation. Let me just make sure I have that covered there. Right. So the sun does not emit low frequency forms of radiation. It tends to it tends to deliver radiation that are high in frequency. And our low frequency radiation bands that are present on the electromagnetic spectrum have been made available to us through inventions and innovations that have occurred over time. All right, so we are going to give some attention to the infrared region of the electromagnetic spectrum. And to do that, we need to have a little conversation about various aspects of waves and electromagnetic waves more specifically. So here we have our bands now. Here is our electromagnetic spectrum, but it's presented with a little bit more detail. The same bands as before, but now we have them being accompanied by the corresponding quantified values of the wavelength. So we have lambda values that are listed here alongside the band assignments. And so you can see that your radio waves tend to be up to 1 decimeter in terms of wavelength. And then your microwave region would be more along the line of 1 decimeter to 1 millimeter. And then moving forward, the far infrared would begin at around 1 millimeter, and it actually goes to just above, just below a micrometer. So not below, but not just below, but right between the micrometer and the 10 to the fifth, 10 to the minus 5 wavelength. Moving forward to the right, we have near infrared, which is between 10 to the minus 5 and the micrometer. And then, of course, the UV, visible, sorry, not UV, the visible region, which again, like I said before, goes from our red to our violet as it transitions across the spectrum. Of course, following that, and in our visible region, what we have is a range of 700 nanometers to 420. So we see the reduction of our wavelength as we go. Ultraviolet region is somewhere around 10 to the minus 7, between 420 nanometers and 10 to the minus 7. So 10 to the minus 7 is what? It's about 100. That's about 100 nanometers. So we're getting smaller. So basically from here to here is about 420 nanometers to 100 nanometers. And then you're going to the actual vacuum ultraviolet, where you can see again the range keeps decreasing. Now I want to draw your attention to these captions that are at the bottom here, because these are the captions that we actually use to help us to understand the impact of radiation on matter. So as you can see, going from the left to the right, what you have is in the microwave region, the impact or the effect of the microwave radiation on matter is molecular rotation, it's rotational. And so what that does is it does have an impact in terms of the molecule, but the impact in and of itself is not invasive to the point of destroying the molecule or picking it apart, so to speak. Moving to the right, what we have is in the infrared region, our interaction becomes a little bit more intense in that what we are having is vibrational interactions where the molecule is not just rotating, it's now getting enough energy, sufficient energy to be able to actually vibrate in terms of its bonds and in terms of its orientation. Moving to the right further, when we enter into the visible light region as well as the ultraviolet region, we enter into the realm where the energy that is available in these bands is sufficient to be able to extract electrons from orbitals and move them back and forth. And so in an excitation, what's taking place is an electron is being removed from an inner orbital to an outer orbital. And then in relaxation, it actually returns back to the orbital that it would have come from, releasing the corresponding light or radiation of a particular wavelength in terms of frequency and color. And so this is what is taking place when you look at your transition metal complexes as they actually interact with various ligands, and you have varying swing that is taking place as ligands pop on and pop off of the actual transition metal itself. So this is one of those things that you definitely interact with when you're interacting with inorganic chemistry and organometallic complexes, because the changes are visible as the interactions are taking place with the radiation that we interpret as light. Okay, so moving forward, what we have is inner core electron excitation that takes place in the X-ray region. So here, what we have is essentially electrons that are actually being able to be removed from orbitals that are actually closer to the nucleus. And of course, as you know, the closer you get to the nucleus of an atom, the closer, the stronger the actual electrostatic interaction is between that nucleus, the protons in that nucleus, and the surrounding electrons. So of course, the energy requirements that would be necessary for extraction would be higher. And that actually then corresponds with why it is that X-ray radiation is able to afford that type of extraction as opposed to the infrared radiation. Infrared radiation does not have sufficient enough energy to be able to access those electrons on the inner core of an atom. And therefore, the interaction is not that destructive where that is concerned. Moving forward, we get to the gamma ray region. And you're familiar with radiochemistry to some degree, I'm sure. And so you're aware that when it gets to this part of the electromagnetic spectrum, the radiation that's present is sufficient enough in energy to go past the electron orbitals and actually enter into the nuclear core of the atom. Now, the corresponding fissions and fusion reactions that are taking place are such that there's a significant amount of energy that's required to actually remove protons and remove neutrons and do all the things that take place within the nucleus and literally change the nature of that species. Now, that's literally the matter being impacted on a subatomic level. Of course, as a result of these types of interactions, we've had significant effects and consequences as a world, as a planet, literally, over the course of history. As you're familiar with the atomic bomb and the nuclear bomb and the various forms of technology that would have been applied in terms of interactions between countries and so forth over time. Just as a point of note, gamma radiation is so intense in terms of its energy level and in terms of its energy capacity that it takes several inches of steel to actually absorb the radiation and literally sequester it, so to speak. And so what happens is when gamma rays come in contact with things like human tissue or plant tissue or anything organic, the destructive nature is significant, which would be the reason why we would have had some of the unnecessary fallouts in history, as I said before. And then the highest energy rays that we've seen here are cosmic rays, which again are along the line of nuclear excitation in terms of its impact and its interaction with matter. All right, so that pretty much brings us to some kind of picture in terms of the effect of radiation on matter itself. And so now we can begin to become a little bit more specific and targeted in our conversation as it pertains to what now takes place in the lower frequency regions. So our area of interest at this time, as you can see, are the infrared regions, because that's where the spectroscopy is of significant impact for us as chemists. So like I said before, here is where you have sufficient enough energy to create vibrational and rotational impacts on the molecules that are actually present as the form of matter that the radiation interacts with. As the high, well, I already said that, so I'm not going to speak to that again, but just note that what takes place when a molecule is interacting with the radiation in and of itself is absorbed by the molecule at whatever level that radiation corresponds to. And of course, there are parameters that determine whether or not that absorption will take place. As you know, interactions between matter and energy are typically quantized. And so that would then explain why it's possible for some interactions to take place and others to not when this encounter is occurring between radiation and matter. All right, so I think the focus for us in this course is to see beyond the macroscopic level and give attention to what takes place when on a molecular and subatomic level, when this interaction occurs as the various forms of electromagnetic bands come in contact by virtue of their energy and their frequencies. All right, so we know that there is an inverse relationship between wavelength and frequency. And that means that the higher frequency radiation waves would have sufficient enough energy to extract subatomic particles and release massive quantities of energy in the process. And like I said before, on the other hand, the low energy radiation, they do not have that level, low frequency radiation do not have that level of energy or volume of energy to be able to extract that type of effect. But what we are going to see is what it's able to do. So here we have a correlation using the equation that we're all familiar with between our frequency, our wavelength, our frequency nu, our wavelength lambda, and the energy itself. Of course, if we actually look at the equation, we can see that energy is equal to Planck's constant, which is represented by h, multiplied by the speed of light or speed of the radiation, divided by lambda itself. Now, we call it the speed of light, which is definitely was measured as that, but it is important for you to know that all electromagnetic radiation moves at the speed of light. So this speed is not unique to the visible light radiation that we are so familiar with. It is actually the speed that all electromagnetic radiation travels at. All right, so this equation is further, can further be modified to give us an expression that includes the parameter of frequency nu. And so we can see the expression of energy in terms of hc divided by lambda, or we can see it as energy equals to hc nu. But there's another correlating relationship between wavelength and frequency. And it actually is one where we can see that in an electromagnetic wave, the expression is such that the speed of the radiation or the speed of the wave is actually the product, is equal to the product of the wavelength and the frequency itself. Now, if you think of the wavelength as being the distance that is traveled by the radiation, one cycle, times the number of cycles per second, that literally would give you the speed. Because as you're familiar, I'm sure, speed is equal to distance traveled per unit time. And so you have essentially, in one wavelength, you have one cycle times the actual number of cycles that are actually being traveled in 1 second, which is what our frequency parameter brings us. So combining these two in terms of multiplication, we get that as the product, and this is the correlation that we need to give attention to. And so the reason we need to do that is because as we actually interact with our spectroscopy components and spectra, we will see that the units that our spectra are actually communicating the signals in, or the outputs in, will not be in those familiar units of wavelength or frequency. And so in order for us to make those conversions, we have to be familiar with that equation that I just had there. All right, so The radiation waves can be reported in the units of wavelength, as you know, and frequency, as you know, where the corresponding terms are nanometers and inverse seconds, right? But for spectroscopy purposes, you will find that there is a new unit that is more often used, especially in infrared spectroscopy, which is referred to as wave number. And the wave number unit is actually derived from the actual quotient of frequency and the speed of light, or the speed of the radiation. So essentially, if you were to actually break this down, you would see that the frequency, which is equal to the number of cycles per second, divided by the speed, would actually equate to this equation here, where this is actually a 1, it's not an I, all right? So wave number is literally derived from dividing the frequency of the radiation by the speed of light, and that actually equates to the inverse of the wavelength, all right? Type a Y in the chat if this is clear to you, or if there are any questions. Now would be a good time to ask. Is this clear, guys? All right, great. So given the fact that our lambda tends to be communicated in terms of meters and more often nanometers or nanometers, whichever one you say, we can then see how it's possible for wave numbers to be conveyed in units of inverse centimeter. And so essentially, as you go forward, you will observe that that's actually what the unit will be when you observe an infrared spectrum. At this time, I'm going to take a pause now and shift gears to give us some information with regards to the infrared region of the electromagnetic spectrum. And here we introduce you to Frederick Herschel. So I'm going to actually stop this slideshow so that I can play the video, because I literally don't know how to play the video without within the slideshow itself. That's a learning curve. Right, so it seems like I stopped sharing, and so let me start again. I don't know why it stopped. Right, so let's take a look at this video so that we can get a sense of how this all got started.
When you gaze at the sky, you marvel at its intensity. Who knows how many stars there are?
All right, hold on a second. This needs to be bigger. Why would you be so small?
This question.
Sure.
Fascinated scientists, philosophers, and dreamers throughout the ages.
Hold on a second. We gotta go to him from a different place, because we don't wanna. All right, so Herschel.
When you gaze at the sky, you marvel at its intensity. Who knows how many stars there are? This question has fascinated scientists, philosophers, and dreamers throughout the ages. One of them was Sir Frederick William Herschel, born in 1738 in Hanover, Germany. Herschel became well known as both an astronomer and as a musician. He moved to England in 1757. Herschel is famous for his discovery of the planet Uranus in 1781, the first new planet discovered in the modern era. But Herschel made another dramatic discovery in 1800. He wanted to know how much heat passed through the different colored filters he used to observe sunlight. He noted that filters of different colors seemed to pass different amounts of heat. Herschel thought that the colors themselves might be of varying temperatures, so he devised a clever experiment to investigate his hypothesis. He directed sunlight through a glass prism to create a spectrum, and then measured the temperature of each color. Herschel used 3 thermometers with blackened bulbs for each color of the spectrum. As he measured the individual temperatures of the violet, blue, green, yellow, orange, and red light, he noticed that all the colors had temperatures higher than the controls. Moreover, he found that the temperatures of the colors increased from the violet to the red part of the spectrum. After noticing this pattern, Herschel decided to measure the temperature just beyond the red portion of the spectrum in a region where no sunlight was visible. To his surprise, he found that this region had the highest temperature of all. Herschel's experiment was important because it marked the first time that someone demonstrated that there were types of light that we can't see with our eyes. What Herschel had discovered was a form of light beyond red light, now known as infrared radiation.
All right, so that's the simple explanation for how we got here in terms of IR. And the reason why that was a significant discovery is because that was the first time, that was the first discovery of invisible radiation. So up to this point, the scientific community was of the impression that all radiation was visible. And so this was a game changer. All right, so so let me continue with what we were saying. Right. So if we are to now look at the general features of spectroscopy, one of the things that you have to be mindful of is that every radiation band that is under observation would be actually subject to examination through some kind of instrument. And the instrument has typically 3 main components. There is always going to be a source, which is the source of the radiation. There is going to be the sample, which is going to be which is going to follow the source. And then there's going to be a detector, which is actually intended to pretty much detect what the transmitted signal is. Now, the idea is that your source is going to actually emit the radiation onto the sample. The sample represents the matter that we are talking about. And based on the nature of the radiation that is in the source, that sample will actually undergo the corresponding impact, whether rotational, vibrational, excitation, absorption in terms of nuclear absorption, or anything else that we have seen on the list that has been presented before you earlier. Now, in the case of the absorption taking place, when absorption does occur, our detector will actually be able to identify what component of the radiation that was transmitted from the source is actually absorbed by the sample. And it does so in the form of what we call a spectrum, okay? So you're familiar with the equation absorbance and transmittance, and that whole picture that comes out as a result of samples actually absorbing signals or what we call radiation. Of course, as we go further, we're going to talk more about that, and we're going to be able to see how spectra is generated from this simple rudimentary makeup here. Further to that, depending on the nature of the radiation, that will determine the degree of sophistication of the instrument. All right, so here we are. Right. So here we are, we have examples of actual instruments. And in this particular case, if you have your PChem textbook, you would know that there's a picture in there that gives us an idea of what the spectroscopy, what the spectrometer is pretty much comprised of. So like I said before, you have your radiation source, you have your sample, and then you have your detector. And of course, your detector is what is responsible for the output that is going to be generated in terms of the form of a spectrum. Again, depending on the nature of the instrument, the degree of sophistication will vary. So I have another video for you all to look at, and I think once we are finished with this video, that's going to bring us to the close of our session today. But it's an important resource that will help us to actually get a sense of what's taking place in spectroscopy, and more specifically vibrational spectroscopy. So I'm going to actually again shift my little slideshow and put it on. But I don't know why. Oh yeah, this might be better. Yeah, this way. Great.
In this online lecture,
Sorry.
we're going to discuss the basics of IR spectroscopy. We're going to see how the machine operates and how it delivers its data. And our key points are, number one, we're going to see different functional groups bend, stretch, and wag at different frequencies. We're also going to learn that, too, a functional group will absorb light if the frequency of light matches the frequency of stretching, bending, or wagging. This is going to be our most important key point. This is the basics of how the IR machine functions. And lastly, what we're going to see here is that 3 IR spectra show absorption bands that enable to determine if a certain functional group or groups are present in a molecule. So let's see how this works. What you see here is the molecule formaldehyde. And formaldehyde just so happens to have something called a carbonyl functional group. That is simply the C that's doubly bonded to the O. We call that a carbonyl functional group. What we need to understand is that if you actually have a sample of formaldehyde, it's not static like what you see here. For instance, let's represent the oxygen right here as some kind of sphere and the carbon also as some kind of sphere. And the double bond between them, let's represent it as this single bond right here. If you were to actually see a formaldehyde molecule, you would actually see the carbonyl bond do something like this. It would actually stretch and compress like this, almost as if there is a spring between the carbon and the oxygen. But that's not the only thing this carbonyl can do. It can actually do something like this, move back and forth like this. In organic chemistry, we call that wagging, kind of like the tail of a dog. So this is the reality of the carbonyl group in formaldehyde. What we've seen is that it can stretch or have what's called a stretching vibration. And let's do this. Let's make up a number. Let's just say it happens to stretch at a frequency of 2 hertz. Now, what does that mean here? Remember, hertz is a measure of cycles per second. So if this is stretching at 2 hertz, it basically means this right here. Let's say we start at this position. The 2 hertz means that it'll stretch 1 like this, and then 2 cycles per every second. Now, keep in mind that's not the reality. It actually vibrates at a much, much higher frequency, but let's keep the numbers simple for now. And also, just a side note here, of course, the vibrations would be temperature dependent, but let's just assume room temperature for our example. Now, let's say we could also measure the wagging, and let's happen to say that it wags at 4 hertz, which again, it means it goes back and forth 1 cycle, or wags back and forth 4 times per 1 second. If that's the reality, then let's see what happens when we take our formaldehyde molecule and we stick him in the IR spectrometer. And let's again label our stretchings at 2 hertz and our waggings at 4 hertz. So here is how the IR spectrometer functions. What happens is when the molecule is in the machine, we take something like this, a light source, which is something that has the ability to shine light at a molecule at various frequencies. On the other side of the machine, we have this thing right here, a detector, and all he can do is detect light. Now, imagine this for a second. Let's say again, our light source has the ability to produce light at various frequencies. So let's say we set our light source to deliver a light that happens to have a 1 hertz frequency. If we shine this 1 hertz frequency light at our molecule, it'll go right through the molecule and hit the detector. And the detector, of course, would say, when you shine 1 hertz frequency light at the molecule, I detected it. We'll see why that happened in a second. But for now, let's graph what we see in front of us here. If you had a graph with, let's say, on the y-axis, the percent transmitted, and this means the percent of light that transmits or moves through the molecule, which would obviously run from 0 to 100%. And let's say for now on the x-axis, you put the frequency of light. So the graph of what we just saw here would look like this. At 1 hertz frequency light, 100% of the light went through the sample and the detector detected that light. Now, let's see what happens if we go back to our light source and now let's set it at 2 hertz frequency light. If we shine this at the molecule, what's going to happen here is the molecule will actually absorb light at that frequency. And this right here is key to understanding how this machine works. Notice the frequency of the light that's being absorbed, 2 in this case, matches the frequency of the stretching. When these 2 things match up, the molecule will absorb the light, which means think about the detector here. His observation is that when you shine 2 hertz frequency light, he doesn't detect the light at all because it was simply absorbed by the molecule. Let's see what this would look like on our graph now. Again, at 2 hertz frequency light, the detector would say not very much transmitted through it. A lot of it was absorbed. So we have a small percent that's transmitted. And that would be this point on the graph. Now let's go back to our machine here. Let's now take our light source and set it at this time 3 hertz. Think about what we just learned here. If this molecule stretches at 2 hertz and wags at 4 hertz, then when we shine the 3 hertz frequency light, it should go right through it. There simply is no match in this case. And the detector therefore would say 100% of the light transmitted through the molecule. So again, going back to our graph right here, we would see that this would be the graph at 3 hertz frequency, 100% transmitted. Now, while we're here, let's do this. Let's connect these dots. This is what we would have. However, let's go back to our IR and let's talk about one more case here. What if we set the light source this time to 4 hertz frequency light? If you've been following along, since this molecule does wag at 4 hertz, then we should expect this light to be absorbed by the molecule. But just to let you know, in some cases, not all of the light is absorbed. And let's just pretend for this case, even though it wags at 4 hertz and it does absorb the 4 hertz frequency light, some of it actually does eventually get through. This happens sometimes in the IR, which means, let's go back to our graph here. If we were to graph this point at 4 hertz, let's say this much percent passes through, which means we would get this point on the graph. And again, let's connect these dots. We'd end up with something that looks like this. What you're seeing here in front of you is basically what the IR machine spits out when you put a sample molecule in the machine. And the vocab here is this. We would call these simply absorption bands. Think about where that term is coming from. It is at these points that light is being absorbed by the sample molecule in the machine. And think about what this means for us. Remember, all carbons and oxygens are the same, and all carbons doubly bonded to oxygens are the same as well. This means that if any sample we put in the IR machine, as long as we run it, let's say, at room temperature, and if the molecule happens to have a carbonyl group, it's going to stretch and wag at 2 and 4 hertz, no matter what molecule it happens to be in. Which means this: if we do run a sample molecule through the IR and we see absorption bands at 2 and 4, we're going to know without a doubt that our molecule has a carbonyl functional group, because it's only carbonyls that stretch and wag at those particular frequencies. For instance, it's safe to assume that, let's say, if the carbon were singly bonded to the oxygen, remember, single bonds are longer than double bonds. So you can think of that single bond as being a different type of quote unquote spring than the double bond, which means if your molecule had a C singly bonded to an oxygen, that bond would stretch and wag at different frequencies than the C double bonded to the O, and would therefore have its own unique absorption bands. So notice what the IR helps us figure out. It simply helps us determine what functional groups that might be present in a molecule. However, let's look at an actual IR spectrum. This right here is the real deal. Notice on the y-axis here, you do have the same thing, the percent transmitted. And notice we also have absorption bands that look like this. Sometimes they're broad like this here. Sometimes they're narrow. And sometimes they're, well, in between. But what I want to point out here is that in the actual IR spectrum, they don't put frequency on the x-axis, they put wave number instead. There's a good reason for this, but it's beyond this lecture at this point. Just know for now that there is a connection between frequency of light and wave number of light. And instead of thinking that absorption bands happen at certain frequencies, we can say absorption bands also happen at certain wave numbers. And just in case, let's know these wave numbers typically on the chart run from 4,000 all the way to 0. Some other basics about the IR spectrum here. Let's know that right about here, from 1800-ish to 4,000 is what's called the functional group region. This is where we're going to look for absorption bands that signal certain types of functional groups in the molecule. And the other side of this region right here is called the fingerprint region. We're going to see that certain molecules have certain absorption bands in this region, and those bands can act almost as fingerprints, meaning that every type of molecule in organic chemistry has a specific fingerprint region with its corresponding absorption bands that are unique to that molecule. Now remember here, the whole basis of the IR machine, again, is that certain functional groups correspond to certain absorption bands that's given wave numbers. And thankfully, the scientists got together and figured out the wave number for all possible functional groups in organic chemistry. Notice this chart here. It's the functional group wave numbers. Let me show you how this chart is read. Notice on the left-hand side, we have bond. So if you're looking at the OH bond, if our molecule was an alcohol and therefore had an OH bond, we would expect to see an absorption band in roughly the 3,200 to 3,650 region. And the intensity of that band, which is basically how strong the signal is, would be very strong and broad. We'll see what this looks like in another online lecture. For now, I just want you to know that a chart does exist with all the functional groups and their corresponding wave numbers. And think about how valuable this information is. If we're trying to figure out what a substance is, a great place to start is what functional groups are present in the molecule. The IR spectrum is going to deliver that information. However, there's one more thing I want to talk about here. Remember, we saw with our carbonyl example that it technically had two absorption bands, one for the stretching and one for the wagging. As we progress through the IR material, we're going to see that functional groups can have many absorption bands. And let's see why here for a second. For instance, a typical molecule in organic chemistry has CH bonds in it. Let's look at the different ways that these bonds can vibrate. For this particular case, one option is you can have something called symmetrical stretching. Another type of vibration here, you could also have something called asymmetrical stretching. Sometimes the bonds can even do this, something called scissoring. And the bonds can also do this, which they call rocking. And it can also get very three-dimensional. This is obviously hard to see here, but these hydrogens can actually twist out of plane, which means from our point of view, the hydrogens would move out towards us. And therefore, the hydrogens would now be not in the same plane as the carbon. Or they can even wag out of plane. We're going to see that a lot of these vibrations have their own corresponding absorption band on the IR spectrum. If we want to do a very detailed analysis on an unknown molecule, then we'd want to look at these other types of vibrations. But if we want to know simply if a molecule has a certain functional group, we can usually get by just looking at only one of the possible vibrations and trying to find its corresponding absorption band on the IR spectrum. Remember, this is just an introduction to IR. We're going to go into a lot more detail in other online lectures concerning this machine. However, what did we learn so far here? Key points. We saw that number one, different functional groups bend, stretch, and wag at different frequencies. And number two, the most important one here, a functional group will absorb light if the frequency of light matches the frequency of the stretching, bending, or wagging. And we saw number three here, IR spectrum show absorption bands that enable to determine if a certain functional group or groups are present in a molecule.
All right, so that is an important takeaway for us. We want to actually now use that. That's going to be one of our important reference videos, because I think it really sets up for us the foundation with regards to IR and the fundamentals, right? Now, from there, what we will do is we will use that information and build on it. But at the moment, the question I want to ask you all is to tell me what is happening with the molecule when, having seen the video and having heard me talk this morning, what is taking place with the molecule upon interaction with infrared radiation? What is the main impact? Type it in the chat as you see fit, please. Not seeing anybody write anything, so I'm gonna have to start calling on people. Asif, tell us what's one impact that IR has on chemical bonds or on chemical molecules. Vibration, I'm seeing persons say vibration, I see rotation. All right, good. So Melina, you're saying bond movement and orientation. Good. So someone can please put in the chat one form of vibration. How does the vibration show up? In terms of the name that has been used to describe this vibration. Wagging, yep. Stretching, okay. And what are the two types of, I was just about to ask. So Lachman is telling us we have symmetrical stretching. So what is symmetrical stretching, Lachman?
Essentially the components, they all stretch at the same, you can say the same way essentially. Like the same frequency, they would stretch the same.
All right, so are they stretching in the same frequency or in the same direction? Or how is the symmetry being observed?
I would say the same frequency.
Same
Because they can be all
frequency.
over the place in the molecule. So yeah, frequency.
All right, so anybody else agree with that? Annalise, what do you think? That's right, it's direction. So the symmetry is in terms of the direction. All right, the frequency has to do, well, that gives me a good opportunity to ask another question. So where does the frequency play in? Asif, are you here? Tell us. Where does the frequency play in? How does frequency play a role in terms of infrared spectroscopy and its interaction with the molecule? Surendra?
Miss, would you repeat the question?
Yes, how does frequency play a role, or what role does frequency play in infrared spectroscopy when infrared radiation comes in contact with molecules?
So I think basically the frequency would determine the energy that the wave possesses, and therefore, since the molecule will only absorb quantized energy, the frequency that the light source is emitting would, the energy that the molecule absorbs would essentially allow for us to detect the molecule, because that particular functional group will only absorb particular energy that corresponds to a particular frequency.
All right. So you're correct. Now, what's happening is, as you can see, infrared radiation spans a particular range of frequencies. And so what that means is that our light source or our radiation source will emit this range of frequencies upon our sample. And as it does that, the sample will absorb some and it will actually not absorb some. So in other words, it's actually very selective about which of those frequencies it will respond to. Is that clear, guys? Melina, I see your hand is raised. Have a question?
Yes, Miss. Miss, I think that I'm carried away with the concept that whenever something absorbs energy, it also releases that same energy. This doesn't the detector detect that release of energy?
Sorry, I missed the last part of the question.
Okay, so you know how like electrons and so forth absorb energy, and
Yes.
then to get back to ground state, it will release the energy. Doesn't the
Yes.
detector detect this release in energy when that happens?
In a way, you can assume that, yes, because, well, okay, so when you're talking about the electrons absorbing or releasing energy, we're talking about the interaction of matter with visible light, right? That's what takes place. In the case,
It's 11 o'clock.
okay, sorry about that. In the case of infrared radiation, the excitation is not taking place on an electronic level, but there is absorption. Okay, so let's just be clear on that. Absorption is taking place across the board, irrespective of what the radiation is. So if I go back to, let's see, if I go back to this slide here, and we look at this spectrum, we'll see that we have various forms of radiation. We have radio, micro, far infrared, near infrared, and so on. Now, every time the radiation comes in contact with the sample or the molecule, the response will be different. The response in the case of microwave radiation is rotational. In the case of infrared interaction, the response is vibrational. In the case of light, it's electronic excitation. But irrespective of what the radiation is, there is going to be an absorption. So to speak to your question, Melina, yes, you are correct in terms of the absorption that's taking place, but in the case of infrared, the absorption of the infrared radiation would not lead to excitation of an electron. It would lead to a vibration of the molecule, right? And that vibration takes the form of wagging, scissoring, stretching of a symmetrical and an asymmetrical nature. So basically what we're saying is, that the molecule actually responds, but it responds by moving, and it moves in these various ways. All right, so I see a question from Surendra. Does the molecule just retain the energy? The molecule, that's a good question. The molecule does not retain the energy. The molecule would translate that energy into a mechanical form. So essentially, the mechanical form will show up in the form of the movement, right? Which is stretching, vibration, which is vibrational. But there's also a corresponding energy form that will also accompany this process, which is thermal. Because as you would know, well, you may not know actually, because I don't think I said it. The infrared No, we didn't mention it. In the first video where we were listening to how Herschel discovered infrared radiation, what he found was that when he actually took the thermometer and put it outside of the spectrum that was displayed on the surface, he found that that particular area had a higher temperature than where his prism had actually been displayed. So what that means is that the infrared radiation has a thermal component that accompanies it. And that electromagnetic radiation that is infrared is heat accompanied. And so to answer the question about the retention of energy, no, that energy is not retained. It is absorbed and it is converted into work. Remember, always remember the fundamental definition of energy. Energy is the capacity to do work. And so whether you have vibration or whether you have excitation or whether you have rotation, all of these are some exhibitions or demonstrations of work taking place. Is that clear? Does that make sense? Okay. So what then happens is the resulting radiation that is not absorbed, right? The resulting what am I saying? Yeah, the resulting, I should be on this one, no? Yeah, no, let's go here. Yeah, the resulting, the result of the radiation that has, why am I saying result? The rest of the radiation that is not absorbed actually will be transmitted at 100%, and the detector will identify it as such. So what we have is a detector or a substance that is able to register the presence of the radiation. So what that means is that our detector would have to be infrared sensitive. It would have to be a detector that is able to register the presence. And I'm going to look at it and see what the specific makeup of our detector is for IR. But it would have to be something that can register the presence of infrared radiation and not just register it, but then help us to quantify, because we know how much radiation we're putting in from the source. And so if there's 100% transmission, then what you would get at the detector level should be exactly what you've put in. But when the molecule actually absorbs some of that radiation, then the detector will indicate that there is a subtracted amount. That subtracted amount would be interpreted as having been absorbed by the molecule through motion. So in this case, the molecule absorbed the radiation and it wagged, or it scissored, or it stretched symmetrically or asymmetrically. Is that clear? Type a Y in the chat if it is. All right, good. All right, so I think at this point, I think we can finish off with this part, and we will just do a little bit of housekeeping to speak to the course outline so that you can have some clarity, because I managed to put it together. So here I am going to, yes, I'm going to do that really. I am going to, yeah, just let me pause share for a moment. I want to put up our course outline, and then I'm going to actually post it on Moodle so that you guys can have it and follow along. These two videos I'm also going to put there on the course page so that you can refer to it as well. 205, where are you? Yeah. Okay. Where is my, oh, no, it's not. All right, so I've set up pretty much the timeline for the course, and what you're seeing here is pretty much what we've covered. Well, this is actually a mistake. This is not supposed to be here. So let me move that. If you want to do some reading on this material, what I'm going to do is I'm going to identify sections in Silverstein. And in fact, that's the main text that I'm using to guide us through in terms of not just the theory, but problem questions and so on. And so what I will do is I will reference pages in that. The text that I have is the 6th edition. I believe there's a 7th edition out. If you can get your hands on that, I'm not sure what the differences are between the 6th and the 7th edition. I don't expect it to be major. But what I will do is I will actually refer you to pages in that text so that you can follow along with some of the highlights. Let's see, I just saw a message here. I don't have a soft copy. The copy I have is actually a hard copy. I know Dr. Fox has a hard copy. Perhaps there's one in the chem library. Check and see if there's anybody in the department that can at least help you to access it, look at it, take a picture of it or something so that you can be able to reference it. I'm not using it like a Bible, but at the same time, it is the main text. All right, so we are here. As you guys know, we are in week 4 of the semester. And so that means we have pretty much some hours to make up. Now, what I will do is I will make sure, or I'll do my best to make sure that we have as much time as possible in terms of the 13 weeks. I don't want you guys to be compromised where that is concerned. So we will take our time, but at the same time, like I said to you before, you have to follow along and be as much on point with this material as possible. So what we covered today is literally hour 1 and a great portion of hour 2. The only thing we haven't done are the selection rules. And so when we come back next class, that's what we will be giving attention to. Between now and probably the next couple of days, I will be posting a worksheet for you to do so that when we meet on Monday, we will be able to work those questions and begin to apply what we've learned to the molecules that we've come in contact with. All right. So in any case, I'm going to post this as well on Moodle so that you can have it and follow along. But as you can see here, after hour 8, that's when we should be having our first test. Hopefully, if all goes well, we'll be able to do that. Yes, I will do that. I will put the chapter name and number. I think in my case, it's chapter 3. In my case, the 6th edition is chapter 3. And since we're starting with IR, that's where I'm focusing on. The language is a little bit, I wouldn't say sophisticated, but it does get far fast. So you have to be attentive and you have to write notes as you are writing it to make sure you have a good understanding of what's taking place. All right, guys, so I think we've pretty much covered everything. So look out for the updated course outline and links to the videos that we saw today, as well as the slide presentation that we had. All right, so I'm going to release you, and that's pretty much it for today. If there are no questions, we will stop